All right, we got this. This is gravitational waves that have been discovered to greatly understand the fabric of our universe. If y'all don't know, I am very, very into science. But we about to get into it. Hopefully this video comes up because I know PBS and like BBC News, they probably like take down the video. But hopefully I'll be able to upload the video and it'd be cool. Gravitational waves, man. We're discovering that the universe isn't just empty.
Let's expand our horizons a bit wide.
I think the fabric of space is the things that we can't see, the particles and the energy around us that we can't see. Because if you look about it and everything is moving, that kind of like shows that the universe is a big soup of particles and energy that we aren't used to seeing. Because if it's nothing there, we wouldn't be able to do anything. We wouldn't be able to transfer energy. We wouldn't be able to do anything. So basically the transfer that happens with like light and like traveling through space is just the leftover particles of energy that we can't see, that doesn't interact with our family of particles. That's what I get the concept of, right? Because look at the picture. Doesn't it kind of look like an ocean? You can't bend nothing. So the fabric of space is something, right? The vacuum of space is something. But what we have, our physical bodies, is just the stuff that interacts with each other the most.
And look at important
The family of particles, positive, negative charges.
Space, time, and the cosmos as we know it. You might remember that Albert Einstein theorized that as heavy objects move through time and space, they create ripple effects in the fabric of our universe. Now, an international team of scientists have detected new evidence of that. Researchers found new signs of gravitational waves, that are affected by huge movements such as the collision of black holes. These are no small matters. Our science correspondent, Miles O'Brien, is here to break it down. So, Miles, Albert Einstein was apparently, 100 years ahead of his time in predicting these gravitational waves. What are they exactly?
Well, they are, in fact, ripples in the fabric of time, and Einstein predicted them in 1915.
Let me think about it for a second. What if, you know how a solid, liquid, and gases? What if there's something above a gas, and the vacuum of space is the thing above gas? Like we have the ocean, which is water and rock. What if what we think of the vacuum of space is the ocean, and the solids we have is rock and gas? Like, you know what I'm talking about? And the vacuum of space is just the higher dimension beyond gases that we don't see, because everything is, as we know it, is a spectrum. And the only spectrum that we see is those three states of matter. And there could be something beyond it, could be something under it. And what's beyond a solid could be the singularity, or could be like the black hole. I don't know.
Were verified by a ground-based observatory based on lasers called LIGO in 2050. So
it was beyond the solid.
What this latest discovery does is prove they are more ubiquitous and found at much longer wavelengths. We're talking about a project called the North American Nanohertz Observatory for Gravitational Waves. We're going to call it Nanograv from now on.
Perfectly.
Funded by the National Science Foundation. They've been working on this for 15 years. I do think it's worth spending a couple of more moments trying to understand gravitational waves before we go much further. Jeffrey Hasbrun helped me out with this. He's at Oregon State University. He gave me a little 101, which we can sink our teeth into.
One way to think about it is if you think about space-time as being jello, right? You have this, it's a little bit more firm than regular jello, but you have jello, and the space in between the sides of the jello gets jiggled by these really massive objects. And so you can imagine, smacking one side of a big giant cube of jello, and a wave would pass through that cube of jello. And so things would compress and expand as that perturbation moves through the chunk of jello.
So he paints quite a mental picture there. Help us understand the scientific significance of this.
Like, there's space, right? They say the atom is like super tiny, right? Whatever fraction it is compared to the electron cloud around it. That little dot controls an electron that's a light year away a marble a light year away of electron. What's in between that? That can be the other family of particles that don't interact with the proton and electron. It can be stuff that doesn't interact with that. And we don't know what it is because it doesn't interact with us. You get what I'm saying?
Well, so the Earth-based LIGO,
it's not empty,
laser
it's just
beam
not interactive.
observatory that I was telling you about from 2015,
That's
was
a lot
akin
of space
to
in between
Galileo
that.
pointing his telescope at Jupiter. Now we're talking about much more complicated and larger telescopes, if you will, looking at other wavelengths. In this case, a wavelength that can be a light year long or longer. And scientists have long hypothesized that if there were gravitational waves, there'd be kind of this background hum of gravitational waves out there. But it was impossible for them to detect them with any sort of ground-based observatory to see these sort of ripples in space-time at that magnitude.
I'm really struck by the quixotic...
And also how some people look at electron. Electron isn't like one cloud, or it's not a one specific particle. It's like the probability of it being in that area around the electron, around the proton, right? So the concept of an atom is not what we think it is. It's the probability of an electron being around a specific proton at a specific time in a specific location around that. The stability of, it's not an orbit, it's just a probability.
Nature of
it's hard. Science is different.
Trying to find
way
out
different
if
than what we live in.
hum rippling throughout the universe. How did these scientists do their work?
Jeff, if you can imagine an observatory about the size of half of our galaxy, if that even computes with you, they took advantage of pulsars. Pulsars are dead stars. They're very dense, about the density of our sun, the size of our city. So Nanograv used a technique called pulsar timing array, which means they use pulsars, which are dead stars, which have predictable kind of rotating beacons, and you can really set your clock to it. And if there's any change in those, you can infer there's something happening. In this case, a gravitational wave, which is changing it ever so slightly. So they trained several radio observatories on our planet at 68 of these pulsars, and were able to pick up these subtle changes and thus identify what they infer to be these big gravitational waves.
These ripples in the fabric of time, do scientists know what causes them?
Well, they don't know for sure, but they think that big, supermassive black
Super
holes
objects
have something to do with
strong
it.
enough to move the fabric.
The universe is a rough place, Jeff. Things are bouncing around a lot, banging into each other, including black holes. And the idea is that as this happens, this is kicking out these perturbations which create these gravitational waves. But I am now officially getting in deep for a history major. So let's go back to Jeff Hasbroon, Oregon State University, for his best current hypothesis.
It's most likely from an ensemble of millions of black hole binaries, supermassive, gargantuan
ones that rotate around each other,
that live at the centers of galaxies. When two of them settle in after a galaxy merger, that's when they give off the gravitational waves that we're looking for.
Okay.
But we aren't there yet.
So he says we aren't there yet. So what's next, Miles? What questions do these scientists hope to answer?
They've identified the chorus. Now they want to home in on some individual singers. And in so doing, they hope to connect the dots a little better between these bouncing around massive black holes and these long gravitational waves. And in so doing, create sort of a cosmic archaeology, understand more about how the universe formed and where it's going, and doing that by listening to the hum of the universe.
Miles O'Brien, always enjoy speaking with you. Thanks for being with us.
Okay. What I was saying, like, I feel like the older I get, the more that I start to like put some pieces together. I'm really starting to think that our universe is a bubble, a fine containment of gravity, energy, all that contained in one firmament, one dome, one bubble, and everything that happens inside of it is a condensed amount of energy where gravitational waves bounce around and they interact with each other because they hit the side and they bounce back. It's like it's a contained explosion. It's bouncing back and forth until it gets smaller and smaller, and particles become those energy waves that stabilize inside of that contained bubble. You get what I'm saying? I don't know, man. I think about this stuff all day, almost every day. I think about these things. What if we are inside of a black hole, but a black hole isn't what we think it is? It's just a new universe that has a contained amount of energy inside of it. And once it like is created, it starts the whole process over of a fixed amount of energy where the fabric is the gravity around it, which interacts with it. I don't know. You get what I'm saying? You want to talk about it in the comment section? Let me know. And I see this video right here. I might have to click this too. Scientist picks up shock waves from colliding galaxies. Ooh, we going on that next.